Hello and welcome to Sustainable Horizons. I'm your host, Jim Woodcock, and today I'm talking to Valentin Storz from Nano Dimension. Valentin and I last spoke at RAPID TCT. That video is available on our channels now. During that conversation, we were talking specifically about the Dragonfly 3D printer, which is a printed circuit board additive system, so it replaces printed circuit board manufacturing. We're here today to develop on that conversation, learn a little bit more about the applications, how it can and is used. Valentin is veteran, do we want to say industry veteran, experience, from MakerBot, then at Stratasys, and now at Nano Dimension, where he is the general manager EMEA. So Valentin, when we last spoke in Los Angeles, we talked about the Dragonfly 3D printer. Could you give us just a quick overview of what we talked about there in terms of what that printer is and what it does?
Yeah, thank you, Jim, with great pleasure. Nano Dimension has pioneered what we call additive manufacturing of electronics, or AME, or 3D printed electronics. And it's a process that comes in the form of a system that is now in the fourth iteration, therefore called Dragonfly IV. It's a process where at the same time, over inkjet printing heads, conductive material and the dielectric material are jetted and then cured. So three-dimensional electronics are created. It's a different process than conventional PCB manufacturing, where you have etching, electroplating, drilling. We only put material where it's needed in an additive process. And that's the beauty of it. And in the beginning, you have the digital files, which are today mainly Gerber files, vias and drill guides, or ODB++ files that are commonly used in the PCB industry. You upload them to the system, you push a button, and then in thousands of layers, the buildup is sliced, as in every 3D printing process. And then on the other side, a functional PCB is coming out. And we are able, by this process, to define for every voxel, three-dimensional pixel, if it is conductive or dielectric. That means things that are challenging in conventional PCB manufacturing, like building many layers or having buried or blind vias, are coming very natural and with no additional cost. And the Dragonfly system is in itself a closed system that doesn't need any additional supplies or tools. It produces the complete printed circuit board. It's a 3D printed circuit board in one step.
And what are the materials that go into the system then? What do you load in order to get your 3D printed PCB out the other side?
So one is a dielectric material, which is a photopolymer material, proprietary material that has similar properties like standard material used in the PCB industry, like FR4, for example. And the other material is a silver nano ink. This is also the origin from Nano Dimension. That is in a solution. There are nano silver particles. It's printed. The solvent is vaporized, and then we have the silver, which is then sintered and fused together by a heat source and IR light. That is in the same process. So if you look into the details, there are two printing heads, and after the printing heads, there's a curing station with UV light and a curing station with IR light. Okay.
And we're talking not just nano in terms of the printing ink, but the whole process is very small scale. You look at a PCB, and some of the components that are added to PCBs are very small and getting smaller. So how does the accuracy compare to, say, a traditional technology in terms of those very fine details that you're able to get?
So we are able with the current inkjet technology to come to 3 mil, which is 75 microns for the lines. we are much more flexible in the build-up, in the set height, because every layer is 2.5 microns, and it can be a multiple of that. At the moment, we typically would say that you need 15 to 20 microns height of a conductive layer to be on the safe side of the design route. There are some processes in the PCB industry that will have finer details going to 2 mil, maybe 1 mil. But what we can do is at ease making a high layer count, 20 layers, 30 layers, 50 layers, for example.
So I guess a lot like other additive manufacturing processes, then you really need to design for the process to get the most from it. If you just try to 3D print a PCB that you've made traditionally, you probably won't be extracting the maximum benefit from the system. You need to look at the design of the PCB and, like you say, how you can integrate into the design the flexibility in terms of layers and building up as well as building across.
Yeah, in the end, there are 3 key areas where the technology is delivering benefits. So the first key area is time to market reduction or rapid prototyping or in-house prototyping. While in the 3D printing and the mechanical engineering, it became completely normal that everyone has a 3D printer on their desk or in their department. This is not true for PCB manufacturing. Typically, one would design the layout and then send the files to China, where they are produced, and it takes 48 to 96 hours, depending on the layer count, and then they fly them over with an aircraft to test it. So what we are offering is essentially the opportunity for a hardware designer to put a design on a machine, have it overnight, have the next day ready for testing, without the need of giving it to an external supplier, raising a purchase order, without the need of physically sending the parts via aircraft from China to the location, and having the ability to even test different designs, like test 2-3 port designs on one tray, and be more agile, allowing for agile method of hardware development. So this is the advantages of time to market reduction in-house prototyping. The second piece is, as everywhere in 3D printing, there's sweet spots. So let me start with what is not the sweet spot. It's 1-2 layer boards you will have in your washing machine. They are so cheap today. Boards like this size will cost $30-40 cents, and the flying them via aircraft is also on the cost parameters, not on the carbon footprint, but on the cost parameters, insignificant. So there's a huge industry, mainly in China, that is super optimized for absolute low cost production. So where do we get into the sweet spot? It's starting with the multi-layer boards, 6 layers, 8 layers, and it really gets impactful when we are at 10 layers or more. Those technologies are used for aerospace, defense, complex medical technologies. Similar like everywhere in the additive manufacturing, you can look at the price or the cost price per weight unit, let's say kilograms. And if you look at the device for AME that is relevant, the total weight of the system needs to be about $5,000 per kilogram. So a washing machine has $7 per kilogram. Tesla has $40 per kilogram. Lockheed Martin F-22 has about $7,000, $8,000 per kilogram. And in-ear hearing aid has $50,000 per kilogram. So one needs to look in the things that are small, highly integrated, that require special functionalities, or the integration of sensors, will allow for cost-efficient production. And I can elaborate later on some examples from medical or from aerospace that are fitting in this niche. And the last field, which I think is especially for sustainability highly relevant, is spare part production on demand or digital inventory. There are a few aspects to that. So one aspect is a train or a vessel is breaking down and needs the replacement of part of a PCB or a component. Very often, those components are not lying around, so that there are no PCBs lying around to replace them. So we will need to produce new PCBs in a factory that has huge loads, because you have to produce all the printing forms and the stencils and stuff. If one would be able to replicate the board by 3D printing, then you can replace it on demand. And that starts already today with a customer having an issue that one component on the board is broken, not the whole board. One component is broken. Typically, if it is a 20-year-old board or 10-year-old, new components will have smaller footprints because they got smaller. So how do you put the component then on the board? You can produce an interposer very easily with the technology, fitting on the old footprint and the new footprint, connecting it, and you can repair almost on the fly. Instead of ordering a complete new board or designing a complete new board. Another element is that you take out the logistics with digital inventory. Nowadays, flying things around the world has become the normal. I think it's much more efficient if we send data around the world and produce it at location where needed, when needed. So one future vision could be that your car, that might be a Tesla or anyone else, finds out that some electronics are broken. The car could then automatically schedule a replacement for this component that shall be printed, and then drives to the shop, gets it replaced. And by the way, maybe you even get a text message where your car is texting you that you will be picked up by a different car today because I'm in the shop for doing the replacement. Instead of having long cycle times and then ordering boards or having high loads of inventory that are never used.
Okay, so certainly from a sustainability point, there's the manufacturing at the point of need is a big one. Reducing the air miles on those PCBs. The flexibility of design as well could open up new application areas for people. But just tracking back to a traditional PCB, how is that? And they're obviously manufactured at huge scale because everybody's got a washing machine and most people have got one or two smartphones and smart televisions and maybe a Tesla if you're lucky. How are those traditional PCBs manufactured as it is?
That's an excellent point. So the PCB production process is not a new process. It's 80, 90 years old. It's done with very modern machines. But the process is old. And the process consists of 70 steps, which include drilling and etching, electroplating, a lot of water, where all the waste is then collected and the water needs to be recycled. It's wet chemicals in use. I don't know if you have been to a PCB factory, even though they try, there's some areas that are very dirty, not only in the terms of environmental, but visually dirty. And we reduced this 70 steps in the PCB process to basically one machine. We had done 2-3 years ago, with the help of companies from the United Kingdom called HSSMI and Fassonil, a study comparing the environmental impact of the use of a Dragonfly system compared to conventional PCB manufacturing. So the thing we are all clear about is water consumption. We don't consume any water. Only the two process materials are going into the process. So there's no water consumed. Now, regarding chemicals and waste, there's a small bottle of waste coming out after many hours of printing. The study found that it's 99% less waste. You might argue with me, maybe it's 95 or 96, but it's significant less waste. We use significant less chemicals, and we also use significant less raw materials because we only put material where it's needed, while in a conventional process, everything is drilled out and taken away. And comparing the also energy, the energy use is significantly less that we have in the process. There's no pressing and heating stuff. When it comes to the CO2 emissions, I think like in the study we found it's between 90 and 98%, let's say 94% less CO2 emissions. That will depend how you calculate it, but very visually, most of the printed circuit boards, about 90% are coming from the Far East today, globally, and most of them are coming from China. And all the boards delivered to the United States and Europe, 99% are delivered by aircraft. So there's a huge tourism just to fly the boards, because people don't have time to wait 3 months on boards, and the conditions on sea might affect that, for all kinds of installations. So we try to give potential savings in let's say normal terms by the use of one Dragonfly under full production compared to conventional PCB. One could save 48,000 liters of water. That would be the equivalent of 48 bathtubs of water. About 210 liters of hazardous chemicals that can be saved just by the use of one system. And one factory might have 10 or 50 systems. We estimate 150 kilowatt hours of energy saved per year by the use of one system, and about 100,000 kilograms of CO2 saved per year, which is about 28 typical passenger vehicles, just by the use of one Dragonfly system. So there's a potential future vision that we can reshore electronics production to North America and to Europe, taking away all this air flight traffic, but doing it in a sustainable way. And assuming mass adoption of the technology, this could have a vast environmental impact on global supply chains, but also if you look at the point of additional digital inventory, saying you could have also the sustainability cycle expanded by having always the ability to produce the parts that are needed, because once you had them in production in a file, you can store them in a digital inventory. You can have even versionings happening out of that with adaptation to newer components that would allow them to keep products moving for a long time.
Okay. So in order to move that manufacturing, obviously you discussed earlier how there's definitely a sweet spot for the technology at the moment in terms of where it can really impact, and that isn't on the very few layers of a PCB. Do you foresee a point in the future where the system, or an evolution of the system as it is now, could replace more of that scope in terms of replacing more of that traditionally made PCB? Because obviously one of the things that we talk about is, of course, that environmental sustainability, and the other side of that coin, and they have to go hand in hand, is commercial sustainability. And both of those are very complicated. So if you're getting 99% of your product from one country, from China, then the potential for disruption in those supply chains is high, especially at the moment, and probably increasing. So from a commercial point of view, yes, it's cheaper to go to China, but there has to be a point where you think, well, it's going to be slightly more expensive to make it in the USA, but it's there. I can see the machine. I know I'm going to get my PCB at the time that I expect it, and with no shenanigans.
Yeah, I completely understand, and it's an excellent point. So first of all, how do we approach the market? Imagine the PCB market is a $75 billion pyramid, where on the bottom you have the lower end washing machines, one layer boards,
Mm-hmm.
and on the top you have the high layer count complex stuff. So we entering from the top, and we industrializing the production technology. So we will go deeper in the pyramid. How deep, I don't know yet. But we will probably never reach the bottom, because if you have units produced by the millions or even billions, then there's cheaper ways. And I can tell you from my experience, we saw it with COVID happening, disruption of supply chains. There was a huge push into supply chain resilience and then having redundancy and everything set up. Quickly, when the economy was up again and supply chains are running again, it's becomes only a cost argument. So it's, I think, the question of balancing the priorities, and it's also a government and macroeconomic task to set the right incentives for the old countries, Europe and the United States, to reshore manufacturing. Only if this is that, then short-term priorities of certain companies and managers that are driven by profit will be affected. And I think the United States are doing already a pretty good job in reshoring.
Mm-hmm.
We foresee more and more coming out of the CHIPS Act, and then what is around it for the electronics manufacturing. And I personally believe that the real benefit of this technology, like additive manufacturing, will lie in if I can integrate several assembly steps into one product. So instead of having different functions on different systems, to integrate all in one systems, that's smaller, lighter, more dense, and reduces assembly steps. But that will require a little bit more education, because today, electrical engineers and PCB designers, they learn how to design for the existing technology. So they will optimize designs for the existing technology. It's all two-dimensional.
Mm-hmm.
You build every layer and then connect it over years.
Okay. So in terms of what else is going on within Nano Dimension, how big a topic do you see sustainability from your client base? How much of a conversation point is it? And do you think that's changing one way or the other, depending on the macro geopolitical climate and the economic climate in certain regions?
So excellent question. So I think, first of all, sustainability is now also connected to resilience. So if you don't have resilient supply chains, you might end up spending vast amounts of money and vast amounts of CO2 just to get one part delivered at your site. So that's changing a bit. Overall, Nano Dimension expanded into electronics manufacturing and into additive manufacturing. And over that, we have our software solutions with Deep Cube and Additive Flow, in which we aim to optimize all processes of our machines or even other machines, increasing the OEE, overall equipment effectiveness, reducing waste, reducing downtime, and basically improving the process, improving the output, and decreasing the cost per part. that is coming out. So the conversations are driven by sustainability. However, if you can't match the cost, sustainability is a condition, but not set into effect as long as the cost is not matching the need. So we drive in bringing down the cost per part. We drive in optimizing the production process and bringing down the total cost.
And do you think that the message around resiliency and the commercial side is more important in the US market versus the EU market? Because we're seeing a lot more regulation pushing manufacturers in the EU to take on sustainability as a real challenge within their business. Depending on what happens in the US, obviously it's an election year, so things can always change. That may be more or less similar to the EU.
I would say we don't see a real geographical difference. There are companies that have ESG regulations, compliance systems, goals in place. So I think it's more driven by the actual company, by the actual management that is setting the priorities. Our advantage in general is that I think we talk more with the people that plan out the future, because they're looking into new technologies, than with the people that are last man standing in the industry and trying to optimize the last few percent, squeeze it out. So probably I'm biased because I have the great pleasure to speak with people that are more driven about sustainability and future competitiveness than mature industry.
Okay, fair enough. And I just wanted to ask you about the James project. So I think you're a board member, aren't you, at James, which is the Additive Manufacturing and Electronics Working Group, I guess we'd call it, maybe. Just hopefully we will speak to them independently as well, and maybe get somebody on to speak specifically to their workings. But what is your involvement in that, and what are the overall aims of that sort of organisation?
So James is a joint venture of the German company Hensoldt. Hensoldt had many names in the past, and they're focused on sensors and avionics, with the goal to drive innovation in the field of additive manufacturing electronics and create a marketplace or platform similar like GrabCAD in the mechanical world, where people can share designs and educate themselves. So, and it's even more relevant for the electronics industry because one can design 3D printed components, capacitors, inductors, or even resistors, and also small subsystems or modules. So in a future vision, one can upload a small system design for a sensor, for example, with defined sockets, and this can be then implemented into a board or electronics design. Instead of defining everything yourself, you can learn. So the idea is to have the marketplace platform available, which will then drive faster market adoption of the AME technology, advancing it far beyond what we have today, bringing the technology readiness level for many products up the scale pretty fast. And that resulted into James as an entity. Before that, we had a great cooperation with our partners from Hensoldt, working for many years on the latest advances of 3D printed electronics.
Okay. Well, an important goal, like you say, the designing for the process, and I guess that change of mindset that's required for existing electronics designers and PCB designers who will have only had one way of making their product, like you say, for 80 or 90 years. It's the same process that's been used for all that time. So it's probably quite well ingrained now into the sort of design thinking of that industry. So as we come to an end, are there any particular, obviously the technology is kind of in its infancy relatively at the moment. It's under development. It's used, I know, a lot by R&D teams to really drill down and get into where the applications for this process might be. But are there any specific applications you think are worth highlighting here now?
Yeah, so one is the field of RF radio frequency. 3D printing electronics allows new degrees of freedom, making non-90-degree angles everywhere, making short distances, connections, building waveguides, lenses, new opportunities there. And we see a lot of publications in this area. We also have seen for RF elements like coupler already production verification, like testing according to DO 160 standards. So it's a field of RF, and today everything has RF, everything is communicating, 5G, 6G, Bluetooth, Wi-Fi. We also see an increase in speeds and data volumes, which is correlated to each other. So the field of RF fits perfectly with market development. Another thing is integrated medical devices. So for example, we have a client that is working on creating pacemakers that are used without a battery. That's, by the way, sustainability of not having batteries is a very interesting thing. So this device shall be powered by the energy of your body. Your cells communicate over electrical impulses, and this is enough to power latest generation electronics. So the device is now pre-clinical testing, but it would be implemented, and then you would never need to replace a battery. While for a conventional pacemaker, you need to replace it every 5 to 7 years. And that could lead to a new generation of electronics, sensors all over your body. So you would be able to start tracking your kidney and liver and get automated notifications on preventive or predictive maintenance of your body.
Mm-hmm.
And the latest application that we see that is fascinating is from the realm of quantum sensors. So quantum sensors is what I believe the most real or most mature field of quantum technologies. And here we see great advances in the packaging. Quantum sensors are used for all fields, starting from medical applications, chemical applications, optical applications. And quantum sensors are essentially the next generation of optimized sensor devices after MEMS. There will be quantum, and we will see a ramp up in these technologies. So the goal is that the quantity of 10 to 100,000 of those quantum devices will be produced for sensors in the next 3 to 5 years. But when we are looking down the road for 10 years, we're talking about billions, and the new production technology needs to be there to integrate everything, reduce assembly steps, and move forward there.
Perfect. Yeah, I think the idea of integrated batteryless sensors monitoring your body processes is pretty fascinating. I hope there's a pause button for when you're on vacation if it's monitoring your liver function and fat intake. Probably more stressful to see that readout and results than it would be to have the alcohol or the cheese. Valentin, thank you very much for taking the time to expand on our initial conversation with us today. I'm sure we'll see each other on a show floor at a major trade show in the not too distant future. But, until then, Valentin, thank you very much.
Thank you very much, Jim. It was a great pleasure, and enjoy your vacation.
Merci.